title slide again.
Yeah, maybe that's good. Okay, so let's maybe begin. This is Meera Parish's second lecture on BCS-BEC crossover and imbalanced Fermi gases. So welcome, Meera, again, and we'll look forward to your lecture.
Thanks. Sorry, thanks. So here I am, all the way from Melbourne. All right. So last lecture we were discussing the sort of the basics of low energy scattering and defining the scattering length, and also about how we can get into a regime where the scattering length can be much larger than the range of your microscopic potential, the interactions between your atoms. And so we're discussing that, and what we kind of stopped at the point where I was going to briefly overview the idea of the Feshbach resonance. So maybe let me jump straight to this slide. So I don't know if, I should mention, maybe you already know that the lecture slides should be online from the last time, or at least the lecture notes, if you want to refer to those. So the Feshbach resonance. So basically, what we want to do here, the idea is that this is a way in which we can tune into this regime, or tune a bound state into resonance, and achieve this regime where the scattering length, the magnitude of the scattering length, is much larger than the range of your underlying potential. Okay, so and I'm not going to go into too many details. I mean, this, as I was saying last time, you could spend a whole lecture just talking about the Feshbach resonance. But the basic idea is you want to have sort of an internal degree of freedom that you can use to tune a bound state. Okay, like we have here, a bound state into resonance with your atoms that are scattering. So often these are referred to like this might be referred to as an open channel where atoms are coming in, scattering, and a closed channel, this kind of potential that we're plotted here wouldn't correspond to the potential that the atoms see at large distances away when they're scattering. This is at a higher energy. So atoms sit in this potential, and then they interact with this other potential when they get close to each other. So the key ingredient really here is that like usually if we're thinking about atoms in this cold atomic gas, the free atoms are in well-defined hyperfine states. Okay, but if you think about the actual interactions that they experience, so if I write down the atom potential that corresponds to this diagram that I have on the right there, this only depends on the electron spin in your atom. Okay, and not the nuclear spin. So in other words, you have these kind of potentials. If I were to just write down the general form, I would have some kind of some so-called potential that doesn't depend on the spin at all, and then there's a spin-dependent part, which generically has some kind of form like this, where these S1 and S2 are like the spins, or the spin operators of the electrons in the two different atoms. So spin atom 1 and atom 2. But the key thing here is that, so this is only the electron spin. There's no nuclear spin. But remember that the free atoms are in these well-defined hyperfine states that actually involve the nuclear spin, right? So the point is that then the hyperfine interaction which is a coupling between your each electron spin in your atom and the nuclear spin of the atom, can couple these two different potentials corresponding to sorry, I should remember. So we have this kind of form here. So that means that you can have, say, potentials corresponding to, say, spin singlet or spin triplet configurations of your electron spin. So now what you can have is a situation where this hyperfine interaction, this can actually couple these two different potentials here corresponding to your two different electron spin configurations. Okay, so this is the way in which you can, well, firstly, you can have two different types of potentials here that I have here, depending on your electron spin, and also the fact that you can actually couple them because of the nuclear spin, the hyperfine interaction. Is that clear so far? So yes, this can couple the interactions, couple potentials here. Electron spin configurations, really. So these are the different potentials here. All right, and what's more, so this is the first kind of ingredient. The other thing is that now you can use a magnetic field to vary the difference between these two different potentials. Okay. So what that means is that, or the energy difference. So finally, then that allows you to actually tune this, so a bound state in there's generically kind of, I mean, these are very deep potentials. There's generic lots of bound states in these potentials. So you can tune one of these bound states into resonance with these atoms coming in and scattering in this original potential. You can tune a bound state in the other potential into resonance. And therefore, you can vary the scattering length in that way as well. Okay. So that's kind of all I really wanted to say about this point, that this is the basic idea of how you can tune a bound state into resonance and vary A. I don't know if anyone had any questions about that, or I mean, I would suggest, I mean, there are lots of kind of nice review papers and that you can look up about this, but is there any questions at this point?
Actually, if I could maybe just clarify. So like this is just meaning to say that normally, let's say if the red potential is like a singlet potential and the blue one's a triplet, normally you wouldn't be able to switch into this new state, but because there's this hyperfine coupling, it allows you to do this? And then, okay. And that the triplet and singlet would react differently to a magnetic field, which means you would be able to tune the difference between the two. Okay, thank you.
Yeah, no, that's that's probably, you put it probably more clearly than I did. Yes, that's right. Yes, exactly. Yeah, so the key is, I mean, sorry, yeah.
I was just going to add that the deeper one is usually the singlet. That's why, so the singlet one is the one that, the key point is one of them allows a bound state, nearby bound state, and the other one does not, at least in this picture. And so then you're tuning that bound state of the singlet near the threshold of the triplet. Yeah.
Actually, the other thing I should emphasize is that the picture I'm drawing here is for alkali atoms. So we're, well, say lithium, potassium, and so forth, where you have just a single electron in your outer orbital. There have been similar kind of resonances proposed for other atoms. So in particular, there's the case of an alkaline Earth-like atoms where you have a completely filled shell. So you'd think, oh no, that means I can't use this usual picture of a Feshbach resonance, using the electron spin. But what you can actually use is, or what people have shown in certain cases, you can use what's called an orbital Feshbach resonance, or instead of making use of the electron spin, you actually make use of the orbital of the the atom, whether it's S wave, P wave. So that's kind of another way in which people have achieved this. But the basic picture is, yeah, you need potentials, two different potentials involving different degrees of freedom, and they have to be coupled in some way. So they have to, the potentials essentially are in a different basis, if you like, from the free kind of free propagating states of the atoms. Yeah.
So I had a question.
Sure.
If you have like if you have an atom which is up and which is down, then in both the triplet and singlet, they would have the same like projection along the magnetic field, right? Then like how would you get this Zeeman splitting?
Okay, so maybe we should think about what you mean by atoms that are up and down. Okay, so I guess you're saying, okay, so typically you would like these two atoms coming in, there would be in some hyperfine state, which, I mean, okay, let's say if we drew some kind of okay, here's field energy. Okay, so they have, okay, so you have maybe, okay, I can draw a lithium, which is kind of lithium-6, which is kind of, let me see. So you have something like, hang on, let me see if I got this right. So you have, is that right? Okay, let me not keep, okay, but the point is that you have these, you want to put it in, say, these two lowest hyperfine states here, say. I think I'm missing a few states, but anyway, so these involve both nuclear and electron spin. And you're wondering about whether, you're worrying about when you bring them in, are they going to be in a well-defined, they're going to be completely spin up, you're thinking, or spin up and spin down.
Yeah, I mean, I was thinking that for the Zeeman splitting, you need like the SZ to be different, right?
Yes, yeah. So that would be true of the, so that's kind of true of these potentials, those, right? So these potentials involve, I mean, okay, so these states, that the original states coming in, they involve electron and nuclear spins, okay, coupled together. So they have both sort of admixtures of both of electron and these potentials on the other hand, yeah, they involve just the electron spin, and they will have, like I was saying, given that they can be either triplet or singlet, they can actually have a different Zeeman shift between the two potentials. So you're right. So there's like different Zeeman shifts also between the original atoms coming in, kind of, but also between these potentials.
I mean, you maybe one way to say this. The totals, the magnetic field acts on these potentials through the total spin. And so the total spin, that S1, that S2, in one case is 0. So it's not, the red curve, the open channel. So it's not acting at it at all, at least in the electronic part. And then the triplet one, the blue one, its total spin is 1. And so electronic spin, so then it is sensitive to Zeeman energy, while the red one is not. So I think it's at least to the extent that the magnetic field, the dominant energy, Zeeman energy is associated with electronic spin, that it's as simple as that. One is just total S is 0, so it has 0 projection, while the total S for the triplet is 1, and so then it has projection 1.
Well, why wouldn't we see it split into 3 Zeeman sublevels in the triplet state in the presence of a field?
Yes, I think, Leo, you have to be careful because the S equal to 1 can have, you think about the 0 component, yes?
So there may be this is an oversimplified picture that's being drawn. I mean, really, there's every atom there's already hyperfine coupling, and there's an orbital and the spin angular momentum. So it's significantly more complicated. But so out of that giant manifold of states, which, strictly speaking, none of them are, they're not really just described by purely electronic or purely hyperfine states, because you're in the magnetic field and there's a different geromagnetic ratio and all that. But out of all that large manifold of states, you're picking out just two that are active, the two closest ones that are in resonance. But there are many, many, many other states that are not being drawn, that are just far off resonance.
To clarify, is the red curve? I thought the red curve was for the triplets, and the singlet was the one that had the bound state.
I think typically that's, yeah.
Yeah, sorry, I might have misstated. The singlet one has the bound state and the triplet one. Well,
I don't know, I guess
they're actually very deep.
it's
So they
always,
all
yeah.
have bound states, but anyway, but
Yeah.
I have a question.
Sure.
So, and it might be like a little bit ahead, so we don't have to talk about this now, but you just told us about how we can vary this S-wave scattering length with this Feshbach resonance. You also mentioned orbital, I think you said orbital Feshbach resonances, and I'm
Yes.
not right,
Yes.
but like, were you talking about like P-wave or higher partial wave? resonances?
Okay. No, that's a good question. No, so actually, yes. So in that case, the orbital Feshbach resonance is about the orbitals in the atom itself. So in the two different atoms themselves. So so now we're talking about what the electrons spin, or what the electrons are occupying in the atom. So I was just making a point. So that one I actually have gone through in detail, and so that is actually where you you can use, so essentially instead of having the electron spin here, you have a potential that depends on the symmetric and anti-symmetric combinations of the orbitals of the two atoms. That makes sense.
Okay.
Yeah, well, I will talk a little bit about in my lecture. So you have the ground and excited states, and you have, this is the E and the G, and you have two nuclear spin states. These are the ones that have the orbital Feshbach resonance.
Yeah. Okay. Perfect. I'll leave that to you.
Well, I will not talk details about the Feshbach resonance, but what we can do with that, basically.
Yeah.
And one quick follow-up. So, so I'm not very familiar with this. If there are Feshbach resonances for higher order partial waves, is there anything to like stop me from going into the lab and using Feshbach resonances to like turn off S&P interactions? Say if I want to study like D-wave superconductivity, like, or do people already do this, or?
I think in principle, yeah. I mean, okay, certainly there's P-wave. I think there are D-wave resonances, as far as I know. I mean, I think
Yes, but they're very lossy. They're very, very lossy. Yes. So the problem is that you cannot gain any interest in physics because your atoms are lost, unfortunately.
Yeah.
So the simplest realization of what you want is if you're dealing with fermions, rather than using two species of fermions, so then you have a spin up and spin down, where the most active and dominant resonance, as Meera talked about last time, is the S wave. If you just use a single species, then there's no S wave scattering, and then you're automatically put into the P wave. If there's a P wave Feshbach resonance, then S wave Feshbach resonance will not mask the physics of the P wave. And that's sort of it's actually a proposal that we put forth with Victor Gurari and Anton Andreev of how to realize a P wave superconductor and using P wave Feshbach resonances.
Yes, but the problem, Leo, is that they're very lossy typically. So that's the problem.
But at least for the P wave, it's a single species does it, at least in principle. D wave is difficult because D wave, then you will have to have, two species, and then you will have also S wave as the dominant one. So it'll be very difficult to shut it off.
Yes, but if the D wave is the one that dominates, in principle, you have that resonance. But it's complicated.
Yes, I see. There's a question of why are they lossy? Where would the atoms be lost to? Yes. So I was actually just going to mention that actually, in some sense, when we're doing the Feshbach resonance, it's this fine balance you're doing because we know that the cold atomic gas itself is a metastable state where actually what the atoms all want to do is essentially go into lower lying kind of molecular type states, or eventually to become a solid. And so you're sort of playing a little bit with the fire, if you like, when you start playing with resonances, because you don't really know whether, that could in principle lead to all the atoms essentially decaying into lower lying, well, firstly lower lying dimer states, for instance. So that's okay. I think that what helps, of course, is that you have, in order to get these to access these lower lying states, you need a 3-body type of 3-body collision. It's not enough to just have 2-body collisions because they're elastic. In general, they're not going to be, there's no way in which they can lose energy. You need a third atom to carry the energy away once these atoms go into a lower lying kind of molecular state. The other thing, I guess, so that's one thing there's the question of, okay, you need 3 atoms to do this. So that tends to be suppressed if you have a very dilute gas. The other thing is that the other question is, it's also about a question of matrix elements. Like if the original configuration of your atoms has a large overlap with your lower lying bound states or lower lying molecular states, then they're more likely to decay into those. So what the problem with these P wave and D wave Feshbach resonances is that you tend to, they're so-called narrow in the sense that it's very difficult to get into a regime where you have a nice large and floppy kind of bound state with we've been talking about these large sort of S-wave type of states, low energy, much larger than the range of the potential. What you typically have in these kind of other resonances is you very much quickly go into a bound state that's quite small. And this kind of bound state has a very kind of larger overlap with the lower lying bound states that you then decay into. So that's kind of the game you're kind of playing with these resonances. How do you tune the interactions without getting too close to bound states that then have a large overlap with your lower lying states? Yeah. Okay. All right. Okay. So maybe I'll press on unless there are any other questions about this. But it sounds like maybe some of this will also be discussed possibly or touched on in other lectures. Yeah. So the only other thing, one last thing I wanted to mention. So that's putting aside the actual details of how we actually tune the scattering length in the cold atomic gas. Now there's a sort of this is, if you like, a theoretical, I think it's a sort of a deep theoretical point as well. If we're assuming that we're in a regime, so we're going to still focus on S wave. We won't look at P wave or higher partial wave. We'll just focus on S wave, low energy scattering. What this means then, what we were finding with our scattering amplitude is that, and the fact that we can describe just all the interactions with just a single parameter, the scattering length, that means that what we want to describe shouldn't depend on the details of our potential. So what we want to do whenever we write down, say, a model for our BCS to BC crossover or many body system, or even any kind of, or even few body systems, what we want to do is we want to be able to replace whatever interaction potential we put in our Hamiltonian, replace that by our scattering parameters that we've just talked about, the scattering length. Okay, so how do you go about and do that? So once again, if we go back to this Schrodinger equation, so that we wrote down for our two-body problem, but now we consider it this equation now in sort of more operator form. So rather than writing it down in as a differential equation, I'll just write it like I have a Hamiltonian, I have a non-interacting part. So this is my kinetic part of my two atoms. I have my two-body interaction. Okay, and then here's my state, my scattering state, and then I have my energy here. Okay. Now, okay, so just written in general this, and then now what you can show is that the general solution of this problem is, well, this is the so-called Lippmann-Schwinger equation. Should I write it? Yep, with all the ends. Okay, so you can show then that, okay, in some sense it looks like I'm just rewriting it, but which is what I'm trying to do. So what I can do is I say, well, I can write it as first an unscattered part. So where this psi naught is basically the an eigenstate, if you like, of the just the kinetic part, without the interaction potential. Oops. All right, so that's what that means, this psi naught. And then I have my scattered part, which I can write down as follows. Okay. Right, let me just initially first write it like this. Okay, so it looks like here all I've done is I've kind of rearranged my equation. So all I've done here, you can show that if you just take this part, you know this is the inverse of E minus H naught. You take this, you multiply it by E minus H naught, so that removes that. It kills this term, right? Because I have this configuration, and then I just end up with this equation again, right? Where I've just shifted this over onto this side, and I have the V on this side here. Okay, so you can kind of convince yourself at least that this kind of construction satisfies this equation. Yeah. Now, okay, so you might worry about whether I'm allowed to do this, whether this actually has an inverse, because given that, what about if this part equals 0? So what the trick then really is to actually introduce a very small imaginary part, which we often denote this plus I0 part. Okay. Really, what actually physically, okay, small, okay, as well as it being a small trick, a mathematical trick, it actually has a physical meaning in that it selects out the correct sort of, how do I put it? So it makes sure it selects out the correct kind of outgoing scattered wave rather than so you remember, like before when we were discussing incoming and outgoing scattering waves, this kind of by putting this in here, you actually, you can show, I won't show it here, but you can actually show that you get the correct outgoing scattered wave. Okay, so it does actually have a physical meaning as well. And then this whole object here is essentially, well, a Green's function, or if you like, a Green's operator really, which I can denote as G naught and E. Okay, I can put it with an us plus I0 or whatever, but it's understood that at least this energy, I'll always shift it slightly into the complex plane, so I don't actually end up with these singular points in my, when this doesn't actually end up diverging once I, if this denominator happens to be 0. Okay, so that's kind of, that's the sort of basic structure. And now so you know that it's already starting to look a lot like, it has exactly the same form as the usual scattering wave function you'd write down, where you have your incoming incoming wave and an outgoing scattering wave, outgoing scattered wave. And now what you can do then is you can define what's called a T matrix, or what's called the T matrix. And all it is it's really just defined as, and I take this one here, and it's just defined as the operator that only acts on the original unscattered part here. So you see at the moment, so initially I had something that looks like it, it just involves the solution itself. Now I just take now I actually define a T matrix, which acts on which contains, I guess, everything, and now acts on this original unscattered part, the free kind of propagating plane wave. So therefore now then, okay, so I have this finally. Okay, so I have this solution here. Do I have any questions, or shall I press on? So basically what I'm going to show here, you can show that this T matrix here, this operator here, so it corresponds to a situation where rather than just being the bare potential here, it describes a situation where you have multiple scattering of that potential. So, because you can see now, already the way I've written it like this here, the original form, the way I could construct the actual form of this solution is to actually repeatedly insert this this first term into this second term here, and so then I end up with this an additional term, and then I insert that one into that term. So I end up with basically an infinite sum involving multiple powers of this V here. So what you can show actually is that, all right, so let me just write it down. So yeah, so if you start with, okay, so now we know that we have this psi here. So I'm just rewriting this equation here. So I have this psi naught plus this G naught, V. And right. Okay, so I can rewrite this now as so if I take this over to the side, and then so I have 1 plus minus G naught. Okay, and then I kind of can invert that, so I have this. Oops, minus 1 here. Okay, and so now I can compare this one here with this form here to actually work out what this T matrix is here. So I know that that's also equal to 1 plus G naught T. Okay. Right. And so finally, okay, if you rearrange that, which is useful exercise, you can find that actually this T matrix is just given by this. This is this is what I'm after here. Right, and that's. Whoops, that was my technology not working here. All right. Yeah, so you might be wondering, what am I doing here? What am I trying to achieve? So what I'm trying to, firstly, what I'm trying to, oh yeah, do I have any questions? It's pretty clear. Okay, so, okay, right, good. So what I'm trying to achieve here is I'm firstly showing how, how to, okay, so I've shown how you can write this T matrix in terms of this V. Okay, and why am I doing that? The reason is actually now, the final kind of piece here is that this T matrix is related to the scattering amplitude, directly related, in fact, to the scattering amplitude that we derived before. So, and as follows, so before we had, okay, so we had a scattering amplitude that involved, in principle, well, we only looked at the S wave part. So that just involved only the magnitude of K, but in principle it involves an angular part as well. So if I write it down more generally, so that's just corresponding to an incoming outgoing wave. Then you find that it's just related to this matrix element here. Okay, right? Okay, so what we've done here is now so previously we derived this. Okay, I derived in the S-wave case, as I said, we're only interested in this magnitude of this K. We don't actually have to worry about the the angle between these incoming and outgoing waves. So we don't need to worry about the K. That's actually directly related to this T matrix that we just derived, which in turn is directly, we can write that in terms of this some underlying potential that I've written down here, this interaction potential. Okay, so that's kind of what I wanted to get. So I can relate. So now what I can do really is I can work out how to connect this V here. I can put in principle any type of potential I want, so long as I get out the right scattering amplitude or scattering properties at the end of it. Do I have any questions about this so far? I know I kind of went through quite a bit of algebra quickly here.
There's an algebraic step I didn't quite follow.
Yeah,
When
sure.
you have 1 minus G naught V inverse, and then
Yes.
the next line 1 plus G naught T. Could you show that how that line works?
You mean like how do I go from here to here? How do I make this equal to this?
Yeah, exactly.
Okay, yes.
I mean, they're not, I think
I think-
they're not, one is not following, this last one is not following from previous one. The last one is following from the last line of the previous page, left page.
Yes, yeah. So I'm equating, so I'm equating, let's see, let's call this 1 and this one. Yeah, okay.
I see that now.
Yeah.
Thanks.
Yeah. This is 1 and 2. Well, yeah. Yep. Any other questions? Yeah, so in general, this is going to be an infinite series involving multiple kind of powers of this interaction potential V. So, yeah. All right. So the final thing, and then I'll get to the crossover. Actually, the many stuff is what we want to do now. So I can actually just take this expression and put it in here. And what I'm going to do, I'm going to essentially just take a very simple, I can choose any kind of potential I want, as long as it's short range and as long as it gives me the right scattering length. So I can say, let's suppose I have a very simple potential. Let's suppose I have, the so-called contact interactions. Where what I'm going to do is I'm just going to say, well, let's take this V matrix element here, and I'm just going to set that to a constant, which I call little g here. Okay. So now, okay, I'll go to the next. Let me just give myself some more pages. All right, so yeah, so I have this G now, and then all I'm going to do is okay, I'll just take this. So I'll put it over here. All right, so I have this. So what I want to do now is I'm going to indeed insert this part here, this one here. Okay, so I take this K prime T, and then remember it's a function of E in general, or E plus I theory. Okay, and now I'm going to, so I have on this side in principle, I have this K prime V K, and then I have this other term, which I also need to sandwich here. All right. Okay, so now remember, so this is just, that's just G, first term. this one, okay, so how do I go ahead and do this? What you can do is you can start essentially inserting complete sets of states of these kind of plane wave states here. So what you end up with then, so if so I can insert them, for instance, here and so forth. So what you end up with is actually you can show that gives you, well, actually, what I'm going to do here is actually I'm going to, hang on, there's probably one step I should add here. What I want to do here is now instead consider this as a series as well. But okay, let me come to that in a moment. So I have this G here, and I have in principle I can write this as, let's see. So you have where am I? Yeah. Yeah. So I have this on my little G part here. Okay, and in principle now I have another part here which include. Okay, so maybe I think the easiest way is to actually first, if I write this now as instead of just writing this here, what I would do is I'd write this first as what I'm really trying to do is I want to write this, consider this as an infinite sum here. So this, you can think of it like this as well. And so forth. So that's really what I'm starting with here, and then I'm going to take this matrix element here. So what I want to have here, in fact, this is probably the easiest way to do it, is this plus, and so on here. So now what I have here is this term here, plus now a term that involves Q G naught Q here. Because what I've made use of is essentially once I insert my kind of complete sets of states here, essentially I can make this replacement here where this is just, replace all of these matrix elements by G. It's very simple, it's just a constant. And then I end up with this here. Sorry, maybe I'm taking a bit, making too long here. So finally, what you can show then, so getting to the final bit of this, is this is an infinite series which actually has this form here, which is just the sum over Q. This one here, yeah. Okay, so that's kind of okay. I've kind of jumped a step here and actually summed the infinite series to give you this final result here at the bottom. Okay. So yes, I don't want to dwell on this too much because I should probably get to the many body stuff. But essentially, what I want to end up with finally, okay, so this is. So I want to relate this G to the scattering length here. So finally, in the end, so this part you can actually do, because that's just, so remember G was just this E minus H naught. So I know how to actually, these are just eigenstates of my H naught. So I can just replace that by the kinetic energy here. And finally, what I want to do is, so remember I have this energy floating around, this energy of scattering, but all I want to do is be able to relate the scattering parameters to my potential. So all I have to do is basically, I can choose whatever energy I want. The easiest one would be just to take zero energy. That's what I'm interested in. So take the case of zero energy. So take E equals 0, okay? And in that case, what I know exactly what the scattering amplitude is when I take the case of zero energy. So do you remember what's the scattering amplitude in the case of zero energy scattering? What does that correspond to? Okay, maybe
Scattering length?
Scattering, yeah. Or the inverse scattering, yeah, the inverse scattering length. In fact, yes, that's right. Yes. So you remember oops, hang on, I wrote it. So yes, exactly. So you remember that for the S wave case, or in general, the low energy case, I had indeed this kind of, well, this kind of form here. So yeah, so indeed, when I take E equals 0 or K equals 0, exactly, yeah, I just get the scattering length out. Yeah. Yeah. All right. All right, so finally then, so what we have, yeah, so we have F equals scattering length, and we have on this side now, we say that this scattering length, or this F, this T matrix here, is equal to the inverse of this. So finally putting it all together, so this is the final step, we have this 1 over G plus this, so remember I've taken 0 energy plus this kinetic part. Okay, and then that's equal to the inverse of the T matrix, remember, so I've taken the inverse of that. So I end up with this 2, and I have, I also need to include all this part here and the scattering length. So I finally end up with 2 pi h bar squared A over mr here. Okay. All right, so the reason I've kind of gone through all of this, really, well, firstly, this is to try and give you an idea of how this actually comes about. That like often this is written down and it's sort of, I don't really see it kind of explained in detail. Okay, oops, sorry. I'm trying to do a little box here, it's not really working. All right, I'll leave it like that. So the first thing is, yes, we want to actually have this. So I'm trying to explain how you actually get this so-called expression that people often use to relate their interaction to the scattering length. Okay. The other thing I wanted to emphasize here is, so this is, okay, so this is the physical parameter that we're interested in here, the scattering length, okay, that we measure. This term here, well, first thing on this side, firstly, what I haven't emphasized here is actually, or what you might wonder about is if you look at this integral here, this is actually a divergent integral. So it actually, if you calculate this, this actually diverges, like, you know, this, if I put in a cutoff here at the top, this actually diverges like this lambda here. Okay, so if I take lambda to infinity, this goes to infinity. So what we need to actually do, if we want to actually have a potential that, write down a potential that gives us a well-defined scattering length, we have to make sure that this G here that we've written down here, this strength of our contact potential actually cancels this divergence here. Okay, so we have to bear in mind that this G actually has to be, it also depends on some high energy scale, some lambda here, in such a way, well, essentially this is the relationship. The way this relationship tells you how it must behave in order to give us a well-defined A. So this G actually goes to 0 like lambda, also like inverse lambda. So it actually can cancel this infinity on this side. So this is the other sort of point. For this G actually has to go like this, which goes to 0 as lambda goes to infinity. Well, this part actually goes to infinity as lambda goes to infinity. Okay, so these are all, this is just to say that what I'm trying to stress here, okay, in principle, there's a real physical underlying potential in your problem, in your gas. The problem is it's a very complicated one. We don't know how to describe it, but we do know how to describe the low energy scattering, the low energy properties set by the scattering length. Okay, so what the trick, what we're doing here is really we're saying, okay, I don't care about what the potential is. I'll just write down something very simple, like this G. I've shown you the sort of procedure in which how you can relate this to your scattering parameters. Okay. And therefore, using that, then this tells me firstly how I can replace it like this using this expression, but it also tells me how these sort of, if you like, this bear or this toy potential should behave if I take eventually I'll take the limit where this, well, effectively this kind of range of this potential goes to 0. Do I have any? Okay, so I'll stop there and I'll see if, do you have any questions about this?
So this is all for 3D, right?
This is all for 3D. That's correct. Yes.
Okay.
Yep. No. Yep.
Is that contact interaction, is that supposed to have like a delta function between K and K prime?
Yes. I mean, yeah, effectively it's a delta function, although you have to be a bit careful about delta function in 3D. But yes, you can effectively think of it as it's like a modified delta function, if you like. But yes, it's like, oh, okay, maybe let me put it this way. It's like the limiting case of, I don't know, let's say it could be a Gaussian or square well potential, limiting case of, say, a square well potential where you take the width to 0 and the depth to infinity. Yeah, so it is sort of approaching that.
But I'm asking in the momentum terms, is it supposed to be diagonal in that momentum?
Oh, I see what you're saying. No. So no. Indeed, it's not diagonal. It really is just. In fact, it's kind of G everywhere. I mean, as in it. Yeah. So they're definitely not diagonal. This can be K prime doesn't have to be K. No.
I see.
Yeah.
So if that's the case, then I don't understand the algebra in the 2 lines down from that. I thought we would be like inserting like resolution of the identity between the V's and G naughts.
Yes, that's right.
These, but then we would need to sum over that resolution of the identity for every insertion that we have. We have multiple sums for every.
Right. Yes. Okay. So the key thing here is that actually this G naught, on the other hand, is diagonal. Yeah.
I see.
Yeah. So that's why you only end up with one sum at the end. So you're right. You might have thought that if I insert 2 of these here in between, I should have 2 sums. But then I make use of the fact that this is actually diagonal. Yeah, this one is here, but these are not. Yeah.
Is there an implicit assumption here that I guess the potential has to be weak?
The potential has to be weak. Oh, you mean in the sense of why is this going? I mean, in a sense, okay. I think what it's saying really is, okay, the implicit assumption is that we have a short range potential. Okay. And also, yes, okay, I guess the other assumption in some sense is that we're only interested in, say, one bound state. So we're choosing a potential which only has one bound state. Yeah. So it's weak in that sense.
So maybe in the interest of time, I would suggest, if I may suggest, number one, I don't want Meera to be shortchanged doing the many body physics with these resonant, but this is a really beautiful exposition.
Okay. Thanks. Well, yeah. All right, good. Yes, I think I'll, so I think this is basically, yeah, I think it's sort of a very kind of deep point, which I thought is interesting. Yes, but yes, let's move on to the many body physics, because I think that's kind of interesting. All right. So what we're going to do here, okay, so we're like we mentioned before, we're interested in the crossover from different types of pairing regimes. So what do we assume? We're going to consider 2 types of fermions. So a 2-component Fermi gas. And then so I'm just going to denote them, say, up and down. 2 types of fermions. And for the assumptions here, I'm going to assume that I have, for the moment, I have equal populations of each spin. Okay, so that means that I have, so the densities are the same, so I'll just denote that N. Okay. And that also means that the chemical potentials are the same. Okay, so that's also, I'm going to consider, just for simplicity, a uniform gas, not I won't worry about the trapped case, but that's something that I mean, that it is straightforward to kind of map from one to the other in principle, at least in the most cases. I'm going to consider equal masses. So in other words, M up equals M down. Okay, so that's just M, yeah. In principle, okay, well, I guess that's the scenario which has been realized, and in principle that you could look at unequal masses. I should mention though that actually it's not even clear if you go to very large mass imbalance that you can have this crossover. So this crossover might be unstable. So that's one of the reasons I'm kind of sticking to the equal mass case. So it could be unstable to forming other phases or phase separation or so forth. The other thing is I'm going to assume that I have these attractive contact interactions. So I'm only going to look at S wave again. All right. Okay. So yeah, so this has been achieved with, with hyperfine states of potassium-40, for instance, in GLA, or lithium-6, I think, for instance, at MIT and other places. Now, okay, so what we want to do then is we have a Hamiltonian. Okay, many-body Hamiltonian. Okay, so where I have my, I have my Hamiltonian, and I'm going to consider the grand canonical ensemble. So I'm going to have a chemical potential here. Okay, so I have, let's see, so I can write it down as, so I have my non-interacting kind of kinetic part. So it involves both spins. So I have my kinetic energy, my chemical potential, and then this is my, my creation and annihilation operators for my fermions. Okay, so corresponding to my occupation of these momentum states here. Okay, and I have an interaction part. So I have my G here, and this is how I would write it. So this is just my contact interaction part, and this is how one would write it in this form here. So I have my, I'll explain this in a moment. So I have my scattering term, basically two-body term. Hang on, let me just move that over. Okay. All right. Okay. Okay, so that's clear. So so basically what this corresponds to is so you're taking, say, two particles, two different fermions, say up and down. So it could be two different hyperfine states, for instance. They're coming in at some total momentum Q and relative momentum K prime here. And then what happens is then they scatter into another momentum K here. But the total momentum of the pair stays the same. So the reason, that's kind of the reason I've kind of written it this way, is to make it explicit what the center of mass momentum is for the pair of fermions. This is this Q, and what the sort of relative momentum is for the within the pair. This is this K. So these kind of what we were considering before in the two-body problem is we were kind of not worrying about this. We were just going to the center of mass frame where we didn't have to worry about the center of mass momentum. We were just looking only at these relative momentum parts. Okay. The other thing, actually, okay, I've been a bit sloppy with my volume factors. So in principle, there should actually be a volume factor here once I've Fourier transformed my potential in real space and put it in momentum space like this. All right. Okay, so that's my Hamiltonian. So now, what do I want to do with that? So how do I go about describing the crossover? So this is, of course, a complicated many-body problem in general. But what we want to do actually is we're going to use so-called mean field approximation. And there are actually two ways in which you can think about this. Equivalent ways you can construct this. And so I would start with the first one I would call is this variational wave function approach. So basically, I put a little reference down here. This is just, I'd written a book chapter on the BCS to BEC crossover, just a short one a while back, which you can find in the archive, and which also has lots of relevant references to the crossover as well, if you wanted to look up more about it. Okay, but so there are various ways in which one could actually just go ahead and describe this. So this one I quite like, because it sort of starts with thinking about constructing what does the wave function look like, and how do I go, starting from, let's say we start from the BEC side. Okay. So let's start from a BEC side. How would we describe this state? You can go deep into the BEC side of, where you have very tightly bound diamonds. So what you can do is you say, let's define a boson operator, or rather the operator for a tightly bound state of a pair of these particles. So that would be, so if I have a boson at, say, some particular momentum Q. Okay, so we have, I can write it like this. Okay, move this over so. Okay, so all I've written down here, this is a pair of my fermions, up and down, with total momentum Q. And this is essentially the wave function of my pair written in momentum space. Okay. So it's like before when we were calculating bounds, looking at bound states in real space. This would be, where I take my wave function, my decaying wave function in real space, and I convert it into my two-body wave function, converted into momentum space here. Does that make sense so far? Are there any questions at this point?
We're only considering pair scattering, but in principle there would be like up and down scattering as well, right?
Okay, right. You mean talking about this one. So the key thing is, because we're only dealing with S wave and looking at low energy S wave scattering, that means that there are no interactions between identical fermions. Yeah. So we don't have any up or down. Yeah. Any other questions about this? Okay. So I've now got a bosonic kind of operator. And so now what I want to do then is I will consider, actually what I could do, I can write down my BEC state of these involving operators. So in principle, so BEC limit. Okay, so in principle, I could take like a product state of these operators, at Q equals 0. So having all the bosons condense into the cubical zero state. It's one way I could write it. What's more convenient is actually to use a coherent state. So, oops. Oh, sorry, I don't know. I hope you, someone's banging here. Okay, so coherent state. Okay, so for my ground state. Okay, so I have essentially write something like this. Okay, so I have some kind of normalization factor here. Okay, and yeah, and then I have my coherent state of bosons. And so this is just a convenient way of writing down my condensed state, you know, or bosons all condensing into momentum zero. And okay, even though it doesn't preserve the particle number, you can show, at least in the thermodynamic limit, that doesn't really matter. I mean, the fluctuations in the number is like, well, goes like square root n compared to the average number. So basically, in the thermodynamic limit, it doesn't really matter that you don't conserve particle number. And it also is just at least from my point of view, okay, you can talk about phase coherent, you know, it has a well-defined phase, etc. But from my point of view, it's just a very more convenient way of working with the problem, with treating the problem, these kind of states here, rather than having a sort of awkward product state. Because now what I'm going to do, okay, so I can put in my, use my boson operator here. I can put in this form here. Okay, so, oops. Let me move this over here. Okay. Okay. Right, so I have my coherent state involving all these particles here. Oops. Right, and now the key thing is, what you can do is you can expand this state here. Because now, so the key thing is, remember now we have these fermionic operators. And I can't have more than one fermion in a state, right? So I have the situation, so I have, if I have this squared, hang on, let me just put the spin part, sorry. If I have this, anything, or any power of this, that has to be zero. So I can only keep, the first power of these operators, because I can only have one fermion in each state, right? I can't have more than one fermion. So that actually makes this, a lot easier to write, in the sense that what this means then is that this state here has to be, well, actually, okay, sorry, the first thing I would do actually, yeah, so this state, firstly, what I can do is I can take out, in the exponential, I can take out this sum, this becomes a product, right? So remember, exponential sum, I can just take that out. And so I have now this here. And I can expand this exponential here. And I only have to go to first order because, as I mentioned, all other states will be zero because we have fermionics statistics. So I have this situation here. All right, great. And then what's nice actually is you can see, well, okay, what you find is actually this is exactly corresponds to what was originally, oh, sorry, I should have this. okay, what was originally written down for the superconductivity, for the so-called BCS wave function, for which is describing this case here, on this side here. This has exactly the same form as that. Once I write, let me write it down even more kind of. Once I write it down, this is the BCS wave function that was written down for superconductivity, was just given by this. Okay. All right. So where now you just need to define, well, essentially, if you define your n and your lambda in the right way, this can be exactly written in terms of UK and BK here. So in other words, okay, I'm running out of space here. Let me pull it over into the next slide. So all right. Okay, so I have my BCS wave function where all I need to identify then is that BK over BK is related to this relative wave function here, and I've taken this normalization to be this. And in order for this wave function to be normalized, I also require this this case here. All right, so what we're really showing here, okay, there's a couple of things, well, okay, a few things we've shown. We've started from the BEC side, written down a coherent state, expanded it, and then what we find is actually this exactly corresponds to what was written down in the BCS case. So this would strongly suggest that, I mean, this already in some sense shows you, or strongly suggests that you can have a crossover. There's no, these essentially the same type, these ground states have the same form, or same kind of structure in both limits. You can smoothly cross over from a BEC's type of state that we wrote down initially to a BCS regime where it can describe also weak pairing as well, from one side to the other. You can have a single wave function that describes both limits. Okay, so yeah, so that's sort of a key point here, which I think is kind of interesting. So yeah, so just to say, so this is smoothly connected. To a coherent state of bosons. That's the BC limit. And BCS is smoothly connected to the BC limit. Because you can see also what's interesting about this state is that it can also describe a non-interacting Fermi gas in one limit. So if you take the limit, where this, you just only have this term or this term, essentially. You don't have this superposition. You can describe the non-interacting case. So like where you just have a Fermi C, where you have, say, momenta up to some Fermi momenta. Yeah. Okay. And where this, so note that this V actually, this parameter here is actually related just to the momentum occupation. So we have, so in other words, if you took this, if you wanted to look at the momentum occupation, that actually just corresponds to BK squared here. So in the non-interacting case, then you just have this, if I were to plot this BK squared. I'll just have this kind of step function up to this momentum Kf. All right, maybe I'll pause here. Are there any questions about this?
I guess maybe just a clarifying question. When we talk about this cross, what should I keep in the back of my mind as sort of the defining features that distinguish the BCS and the BEC at the two edges of these lines?
Right, okay, yes, so, yeah, okay, so really, yeah, so what you should, okay, so okay, maybe I should link it back to the two-body problem. What you can keep in mind here is that you should think of like the BCS state, or the so-called Bardeen-Cooper-Schrieffer state is corresponding to, in this particular 3D case where the scattering length is negative, so you don't have a bound state, and the BEC case is where you have positive scattering length, so you do have a bound state. So that's kind of the simple way to think about the two different regimes. But I'm going to mention actually that there is even, well, a bit further on, there is even another way to think about, well, not another way, but you can even define a particular crossover point, which doesn't necessarily, or doesn't correspond to the case where the bound state appears, but it's near where the bound state appears, but it's in the many-body system, it's not exactly where the two-body bound state appears. But roughly speaking, you can think about these two limits in this way. Yeah.
Thanks.
Yeah, no worries.
I have a question.
Yep.
So when you are choosing your coherent state in the slide, the second part, why did you specifically choose Q is equal to 0?
So I want to describe, why did I, so I want to describe, well, okay, the ground state. I want to describe the lowest energy state, and I wanted to, and that's given by,
Zero. I see. Okay.
Yeah, it's just
another question is, in writing the Hamiltonian, is there a specific reason why we're not taking spin polarized interaction terms, for example? Like,
so as I was mentioning earlier,
I think you mentioned this. Sorry, I missed it. So
no, that's okay. So it was, it's because we're considering S-wave scattering only. And in that case, interactions between identical fermions vanish.
Okay. Thank you.
All right. Okay. And is the ground state still a coherent state in between the two limits? Well, yes. I mean, so as far as you know, what we're imagining. Okay. So so this isn't a proof, but what we're the fact that we can write down, the fact that the same wave function describes both limits strongly suggests that we can use this wave function throughout the crossover, so it remains kind of the same, has the same kind of structure throughout the crossover. And as far as we know, so this is of course an approximation, but as far as we know, there is no kind of sharp transition, or there's no kind of sudden change in the ground state in this system. There is really just a smooth evolution from one side to the other. So you can think of indeed they all kind of behave like a condensate of some kind, so, or a coherent state like this, yes. Yeah, so that's kind of key, that you have this crossover rather than a phase transition between different regimes. So I should mention that actually that there are situations, so if you were to consider P-wave pairing instead, which we're not going to consider, but just here, but if you were to consider that actually can have some kind of transition between the two. There is, but in this S-wave case, there is just a crossover. Okay, so Cooper pair often conceived as a bound state of fermions, but here A less than 0 means no bound state. Okay, yes, no, so that's a good question. So yes, so what people often say is they talk about a bound state in momentum space or many body bound state. So the way you should think about it actually, So certainly there's no bound state in the two-body case, so in the vacuum limit, the zero density limit. But as when you have a finite density, what you can have now in that case is kind of pairing happening at the Fermi surface. So okay, so maybe this is something that we'll discuss more in my remaining few minutes. So what might be useful actually is if I plot this the behavior of this VK squared, this parameter here throughout the crossover. So remember, so just before I do that, what I should just point out, so just wanted to remind you that, okay, so for this Fermi wave vector here, KF, it's related to the density. Okay, so you can just obtain that from using the fact that this density is just going to be given by sum up all these, essentially, or integrate over all the different momenta for this BK squared, and that's how you can find what the actual Fermi momenta is. So that's related to the density. So what you find, so now if I were to actually look at the behavior of throughout the crossover thing. Okay, so right, so what we have now, okay, so we have, so like I said, so if you go to if we start now with a very weak interaction, weak sort of, small and negative A, what you find is actually there's a small kind of smearing of this Fermi surface. So this pairing that occurs just around this Fermi surface. And then as you increase the interactions, what's going to happen is that this VK squared. So you remember that this VK when we started out with this coherent state of tightly bound bosons, and in that limit it's related to the wave function of the tightly bound pair. Okay, it was proportional to that. So what you're going to find is that this kind of smoothly crosses over into the wave function of a tightly bound pair. So that's something now that's going to look something. Oops, try and draw it properly. Something that looks like that in momentum space. So we have something that maybe looks like this, and then it smoothly kind of crosses over to that. So it gets more and more spread out. Okay, I didn't perhaps do a very good rendering of this, but more and more spread out in momentum space as you increase the attraction between fermions. So you can think of it as you start from a nice well-defined Fermi C or Fermi surface, and then step function, and then you kind of smoothly kind of deform that into a tightly bound pair wave function. Okay.
Sorry. Yeah. So the green curve is for like BEC limit.
Yes, that's right.
Okay,
yeah.
Good. Thank you. So what was the sharp VK square that you drew before at the top of the
this one here? So that's the case where let's say A equals 0. Yeah, so no interaction.
Oh, now okay, cool. Yeah, thank you.
Yeah, no worries. So this is so what so I think I'm running a bit short on time, because what I was going to do next was to actually just show you how you can actually relate all these parameters, or how you can actually go through and derive all the parameters of the BCS to BEC crossover, like how you derive like the pairing and so forth from from this wave function. Because what we want to do now is we can take this wave function, this is a variational wave function, and write down the free energy and minimize that. Okay. And then you can basically end up solving this equation and end up with all the relevant equations for the BCS to BEC crossover, the so-called pairing gap equation and everything. Okay, but what I might do, let's see, given that it's probably about time now. I don't know. My time is probably up. Okay, so yes, so maybe are there any other questions at this point?
So where on this plot is like where the BCS limit is on this plot?
So this first one is like the BCS. Yeah.
Okay.
Mm-hmm. So BCS limit is where it's sort of something that it looks very similar to the non-interacting case. So where you have also let me do it like this. So you have also, chemical potential, which is just given by the Fermi energy, which is this one here, which is just the energy of the at KF. Okay. So so you have these small kind of deformations, small kind of smear, deformations of the Fermi surface. So if you like, you can think of it. I mean, this is often how people might draw it in. If you think about it like this, so you have this is your filled Fermi C up to KF. And actually the way they originally thought about, when Badin Cooper-Schrieffer, actually it was Cooper was trying to think about, pairing in this many body sense, a weak pairing. They were thinking, you can think about the so-called Cooper pair problem, where you have, where you're imagining trying to pair, say, let's put it, K and minus K. You're trying to pair two particles, two fermions on top of the Fermi surface or above the Fermi C. So you can actually go through and, so you can either, so previously you could, if you just looked at the two-body problem, so in the absence of the Fermi C, you would go through, you would solve your problem and you would find that you only have a bound state for, you only have a, pairing or bound, well-defined bound pair for negative scattering length. Now, if you went ahead and you did the same problem, where now you had this Fermi C, you're trying to do pairing and you had this Fermi C, which means now that you've effectively blocked all these states from your problem. Like you can only pair for momenta. You can only have momenta above the Fermi C. Okay. Because of Pauli exclusion, these are effectively all Pauli blocked here. If you go ahead and just do the simple problem of, let's try and solve the two-body problem just in this case, two fermions with blocked Fermi C, you find actually that you always get pairing now for any strength of the interaction, for any kind of A here. You always have something, and by pairing in that case, that means that you always have an energy that's smaller than this, the energy set by the Fermi C, this chemical potential. Or in this case, twice the chemical potential because you have two particles here. So that's kind of one way you can see how you always have pairing. But that's, of course, this is also an approximation. This is this Cooper pair, simple Cooper pair problem. But now what we're doing here is essentially we're trying to do it in a more we are doing it in a self-consistent manner where we're assuming that it's not just one pair of fermions that can participate in the pairing. It can be the whole, the whole Fermi sequence or the whole system can involve in pairing. And that's what you find kind of gives rise to this reconstruction, if you like, of the Fermi C due to this pairing that's taking place that it's unstable towards. Okay. Any other questions? Or I guess we should.
Can I ask a question?
Sure.
So for the plot you have shown here, so it's crossed from the A smaller than 0 to A greater than 0. It's went through this A going to infinity, right? A divergence.
Yes, that's right. Yes.
So
yes.
What is a divergence curve looks like? Does that have a special curve?
Okay. Yes. No, that's a good question. So yeah, so at least in as far as the crossover is concerned, I mean, it doesn't actually, yeah, it doesn't, I mean, this could be, for instance, it doesn't look kind of qualitatively special in any way in terms of like whether it's positive or negative or anything like that. It looks like I wouldn't be like if I showed you a whole series of curves, you know, through the crossover like of this BK squared, you wouldn't be able to see any different. I mean, you wouldn't be able to see anything special happening at that point. What is special about that point, though, the case where, you know, this so-called unitarity regime. So you're wondering about unitarity, which is where 1 over A or equals 0, so A diverges, is that now suddenly your length scale for your interaction drops out of the problem. So now I have, this is what's often called a universal regime, because what that means now is that now all your, so your energy or, you know, thermodynamics only depend on the scale set by the Fermi gas, right? So for instance, you would have something where, say if you're looking at, okay, so generally you have a chemical potential which, you know, which would also depend on your interactions, you know, throughout the crossover. But there, for instance, you'll have a chemical potential that scales universally, you know, I mean, it's universally proportional to your Fermi energy like this. So this is where this is this some universal constant here. And there are also some, this system is also scale invariant in the sense that it doesn't matter whether you kind of lower the density or increase the density, it kind of has the same behavior. I mean, that's another statement of what I'm saying here. There's no kind of scale in the sense, it's only, you know, it's only anything, it all just depends on the density of your particles. Okay, so that would be what I'd say there. I mean, I'm kind of leaping ahead and kind of talking out, talking out stuff that I was meant to get to a bit later after I'd gone through the mathematics, but I think it's good to discuss it now, I think. Okay, does that make sense?
Yeah, thank you.
Thanks. All right, I think probably, unless there are any other questions, shall we stop there? Any other questions? Yeah.
This is all at 0 temperature?
Yes, that's right, exactly, yes. This is all, so yes, that's a good question because, yes, so this is all the ground state properties. So it's true, as soon as you have finite temperature, you won't just have a crossover, you can start to have phase transitions. Yeah. I mean, as in you can start to, now you can have as you know, on the BEC side and the BEC limit, you can have a finite temperature phase transition to a normal Bose gas. And the same kind of can happen here. If you raise the temperature, you'll lose the condensate or you'll lose the pairing. Yeah.
But will the crossover between BEC and BCS also become a phase transition, or like?
Okay, so in the sense yeah, I guess you can think of it that way in the sense that because the critical temperature for the finite temperature phase transition will depend on the interactions. Certainly, if you just if you set fixed at a particular temperature and then you vary the interactions, you will go through a phase transition. But that's just in the sense because, that's just because the critical temperature itself depends on interactions, if that makes sense. So, okay, I don't have my plot here, but, okay, I had to, and let me do it later. So in other words, okay, I'm sort of jumping ahead of myself here, but if you have temperature and you have one over, so here, KFA is here, what you find is that this actually, oops, put it over here. So you have some kind of critical temperature above which you have a normal phase. And so So okay, so say on here you have the BEC side here, so you have some sort of flattened out curve here. Yeah, so certainly if you set at some particular temperature and then you ramped across like this, then you'll encounter a phase transition. But it's a finite temperature one. Yeah. Okay.
Great. So any final questions, or is this a good place to wrap up?
I think maybe this is a good place. Yep. Thanks.
Great. Yeah, thanks for the great lecture, Meera, and I'll see you all tomorrow.
Yep. Thank you. See you.
Thank you.